Hi, this is Fahd Sarfraz, and I'm pleased to present our work on noise as a resource for learning in knowledge distillation. This is a joint work with my colleagues Elaya Rani and Bahram Zanus. While noise is predominantly considered as a nuisance in computing systems, it permeates every level of the nervous system. These multiple noise sources contribute to variations in neural responses to the same stimuli, referred to as trial-to-trial variability. A number of studies in neuroscience consider noise and trial-to-trial variability as salient components of the computational strategy of brain. Similarly, it has been shown that noise can improve the training of neural networks. It is commonly used as a regularization technique by adding it to the input data, weight, hidden units, and the gradients. Inspired by these studies, we aim to further investigate the role of noise as a resource for learning. To this end, we chose knowledge distillation framework as it resembles the collaborative learning between different regions of the brain and enables us to experiment with different types of noise at multiple levels. We first aim to mimic the trial-to-trial response variability in brain, which contributes to the information conveyed by neural responses about the stimuli. Since dropout can be used to provide principled uncertainty estimates for an input image, we propose to use the variability in supervision signal arising from keeping dropout active in the teacher model to simulate trial-to-trial variability. Our formulation, Fickle teacher, involves first training the teacher model with dropout and then keeping it active while providing supervision to the student model in distillation step. The variability in supervision provides additional information about the uncertainty of the teacher model predictions on a particular data point. Our empirical evaluation shows that Fickle teacher consistently improves over the original formulation by Hinton and provides better or on-par performance with state-of-the-art distillation methods. It also complements the other distillation approaches better. We then explored variability in stimuli for improving the reliability of the model under malicious attacks by adversaries to fool the network. Gaussian noise injection in the input image has been shown to provide robustness to these adversarial attacks. However, there is an inherent trade-off between robustness and generalization. As knowledge distillation enables combining multiple sources of information, we hypothesize that combining information from a teacher with high generalization while training the student to be robust to noisy input can reduce this trade-off. To this end, we propose Soft-Randomization, which utilizes the teacher trained on clean data to train the student on noisy data, by minimizing the dissimilarity between the student's distribution on noisy data with the teacher's distribution on clean data. We show that Soft-Randomization considerably increases the capacity of the model to learn robust features even with low noise intensities. This allows the use of lower noise intensity for increasing adversarial robustness while keeping the loss in generalization much lower compared to Gaussian augmentation model with comparable robustness. Finally, we explore variability in the target labels. Human decision-making shows systematic simplification and use of heuristics which may lead to suboptimal decisions. We believe that such cognitive biases are manifested in deep neural networks in the form of memorization and overgeneralization, which makes it particularly challenging to train models efficiently on real-world datasets with some fraction of incorrect labels. We propose to use target variability as a counterintuitive technique to mitigate cognitive bias and discourage the model from memorization. To this end, we propose messy collaboration, which incorporates target variability in the knowledge distillation framework by randomly changing the ground truth labels to random targets while distilling knowledge from the teacher. Since the targets keep on changing for each batch, target variability effectively penalizes the model for memorizing and avoids overconfident predictions. Furthermore, the soft targets from teacher provides additional information about the similarities between different classes, which can mitigate the adverse effect of incorrect annotation. The empirical results on varying degrees of label corruption confirm that knowledge distillation is an effective framework for training models under noisy labels and that target variability can indeed discourage memorization. To sum up, our study demonstrates that noise can indeed be used as a resource for learning in a collaborative framework and warrants further investigation. Thank you.